Hello and welcome to TidyX episode 123. TidyX is a screencast where we explain how our code works. My name's Ellis Hughes.
And my name is Patrick Ward, and today we're still in our data cleaning, data engineering phase of tidyverse.
Yep.
Last week we did some kind of time to event and filtering between events. This week we're going to talk a little bit about using functions like crossing to get a whole bunch of like the Cartesian product, basically. You'll see what we mean, but basically you're getting every possible permutation of whatever the heck it is you want to stick in that crossing function.
Yep.
And we're going to walk through how it works. And then we're going to apply it to some made up examples if you were like using player tracking data in basketball or football or hockey,
It's really
soccer,
any
those kinds of
sport
things.
or any sort
Any,
of any sort of thing where you have a time series and you want to compare positioning of multiple people.
Right. When you're interested in the distance or relationship between two players or two individuals or objects on some sort of coordinate based grid, essentially. So walk through an example of that.
Exactly. All right. So let's get going into this because this crossing is something that I've kind of used here and there to kind of help me just kind of quickly build out some data for me to use. Uh, so it was kind of fun for me to play around with a little bit this week and see some techniques and try out some things that maybe surprised me. I thought it would work one way, and I actually found out it worked another way. Of course, you read the documentation; it's all documented and it's all there. But it was just like not immediately what I thought would happen. But then when you did read the documentation, like, well, of course, that kind of makes that makes a lot of sense. So
Mhm.
let's get going here. First, we're gonna load up tidyverse because that is what provides us the crossing function. It is, I think, through the tidyr package itself, but it makes this available. So let's first talk about the basic use of crossing. And so most commonly, you're gonna if you come across crossing in the wild, you're gonna see something kind of like this, where it's going to be crossing and then a couple vectors listed into it. And what that's doing is it's coming up with the Cartesian product of all the different vectors that are going into this. And so for a small toy example like this, it's pretty easy to kind of wrap your head around where it takes every combination of this vector and with every combination of this vector to produce a new data frame that is, in this situation, because it's 3 by 2, it'll be a data frame of 6 rows. And so the A goes to then the 1, 2, 3, and the B goes to the 1, 2, 3 as well. Or, I mean, you could think about it the other way. The 1 goes to the A and the B. Depends on how you want to think about it. But we can run that, and we get our full cross, where it's now got the names myvec1 and myvec2 as the two entries, and it's got this nice little tibble here that has expanded it out. The same logic holds when you add another row to this. It expands now by myvec1, myvec2, and myvec3. So this is now a product of 3 times 2 times 3. And so that brings us up to 18 different rows. So we can run that, and we can see that it's now got entries for example, 1a.1, 1a.2, down to 3b.3. So it's got this expanding nature. So it's really easy if you're like doing a simulation or something like that and you want to look at a bunch of different scenarios to go into your simulation, like as presets. You could maybe set up a crossing with a couple different of the parameters that are going into this and kind of basically do a grid search
Yeah.
across everything.
Pr- Pretty much when I use crossing, it's exactly like that. I've built a model and I want to evaluate how the inputs of that model lead to different outputs. And so I create a massive grid of all the potential combinations of inputs. And then I run a predict of that model over those inputs, and that helps me look at what the output looks like over those simulations. That's primarily the
Yeah.
way that I use crossing. Yeah, for
So
sure.
it's but it's like you look at this and you have a near like, well, of course that's how it behaves. Like it's crossing. That totally
Yeah.
makes sense. What happens
Mhm.
when you enter a vector where there's a duplicated entry though? Where it's now myvec3, but rather than being point 0.1, point 0.2, point 0.3, it does not expand out to 18 records because this is duplicated, right?
Yeah.
Point one is duplicated. And so it's not actually creating a new, it wouldn't be creating a new record if it just blindly went through and looped across everything. So I don't know what it's actually doing under the hood, but like my brain is like, this is basically doing a unique on the vector that's dropping in. And so this is now essentially going to lop that off.
Is
No, that doesn't exist.
And crossing is very similar as in base art to expand grid. I don't know if expand grid handles duplicates like that the same way. I'm not sure.
Scan.grid.
Yeah.
We can throw that in there and see.
Let's see what happens. Ah,
So it preserves it. And so
yeah,
that might be
it
a
keeps
use
it.
case for that, or the like
Yeah.
if you do want all of those records, and I think there is an analog. It's expand underscore grid. Yeah.
Yep.
So expand
Yeah.
underscore grid in
That's right.
tidyr does that. So
Yeah.
crossing
Yeah.
is trying to give you the unique set of crossings across the vectors that you drop in there.
Yeah. That's good to know.
So the next piece is, so we're not always working with vectors, right? Sometimes you might throw in a data frame. You're like, I want all of these records crossed with some other vector or another data frame, for example. And so how does that work? And so, I mean, functionally, you just drop it in just like a vector. But when you do that, it's now going to come up with the unique crossing of this 1, 2, 3, or these three records here with the three records in the tibble.
Mhm.
And so it's now going to produce 9 records because it's 3 rows in the tibble and 3 rows or 3 entries in this vector. So that's only 9 unique records. It isn't the myvec3 combined with the call1 and call2 because the tibble is now seen as a unit and it's done by the row. So we can see that. And then if you want to cross, don't remember what's, oh, right, this is to compare what's going on if you if you have these in just their vector form. You can see that this is going out to 27 rows because it's 3 by 3 by 3, which is 27. Now if you go across the two tibbles, again, this is looking at it row wise, and so it's the rows of this tibble crossing against the rows of this tibble. And so there's 3 rows in this one and 2 in the second tibble. So we're only going to come out, quote only, with 6 rows because of the way that it crosses, where it's the point 1 and true are crossed with the 1A, 2B, 2C. So you can see
Yep.
that how that plays out there. And so once again, it's once you understand how it looks at the data, when you drop it into crossing, it's really easy to see what's happening, what the results are. But if you just see the code maybe and you don't fully grasp how it's supposed to be working, you mean like why didn't this expand fully out and have every single potential combination of this?
Yep.
So the opposite of, so well, I guess not the opposite, but the next piece that you might want to look at instead of crossing is you might want to expand something. So looking at a given data set that you have, and so this is just a table that we created. Probably should have just done this with crossing, where it's 1, 2, 3s and A, B, C, and there's values from 1 to 9. And if we drop out 2 records so that it's not a complete set, so it doesn't have every combination of column 1 and column 2 anymore, so we're missing in this case 1A and 2B, what you can do is you can use this expand function in here. And what that's going to do is it's going to return to you the full set of potential combinations between column 1 and column 2
Mhm.
that could exist, not necessarily that do exist. And so that's a distinction between those two. So you saw that we dropped 1A and 2B, but once we threw it into this expand, it returned it to us because it saw that A was a potential in column 2, and it saw B was a potential in column 2, and in column 1 it saw that the 1 that was missing and the 2 that was missing, still full set combined, we have 1A and 2B back. The almost the opposite of that is the nesting function, which is used inside of expand. And what it does is it gives you the unique combinations of the columns that you pass to it. And so this is giving us the unique combinations of call 1 and call 2. This is duplicating. So this is these records are now, you have 2 records of 1A, 2 records of 1B, and whatnot. But if you pass that in, it's now going to just give you the unique smaller set. Functionally, I don't know how that'd be different from a distinct, but I'm sure there's a reason in a situation where this works, and I'm just being naive and and not aware of the value of this versus this. And I'd love to hear down below if you've got a situation where distinct versus expand nesting, which one worked better for you and why. But yeah, so that's a variety of different ways that you might be using expand to handle growing out your data sets or building it out and trying to understand how, when you put in tibbles and vectors and whatnot, how that combines together. Or if you've got a data set and you want to look at what are the potential combinations between these two. Like say you have a player that's getting some sort of treatment versus not, you want to compare which players are and are not. You could potentially use this distinct or the expand if you've got that information there. But Patrick, let's hand it off to you for a little bit more of a functional example of how this might work.
All right. So when I think about these types of things, I think a lot about player tracking data. So here I just made this little example, toy example of a play. We've got two teams, the Bobcats and the Sharks. It's play one. And each individual, each player on each team has an XY coordinate. So we essentially know where they are on the field. And one of the things that you might be asked to do or might be trying to do with data like this is that you want to know the relationship between each player to, let's say at first, maybe to the opponent, but then also to the opponent as well as their teammates. And so I'll show two different ways that you can sort of handle this. One is using a series of left joins, and the other is using crossing. So we create our little data set up at the top. We use Tribble here, so we can just kind of pass in the values that we want underneath of the column names, which were specified with the little tildes. So we have this thing called tracking data. Usually, if you're doing this on a real data set, you're going to have to join on many variables like a game ID and a play ID and some sort of timestamp so that you know where things are and they're in order. But we'll just keep this simple for right now. My general rule of thumb with big tracking data is start with the most simplest version first and figure out where you're at before you blow it up.
Exactly.
So yeah. So first example, we'll use the crossing function here to solve this. And what we're going to do is we're going to take that tracking data, we're going to pipe in that tracking data to itself. So remember, we're now doing our Cartesian product on itself, the data frame on itself. And we use this .name _ repair equals universal function because if we were to just run this by itself, what happens is the names are all the same, and we essentially of the columns are all the same, and we essentially break things, don't we?
It yells at you because it doesn't want, when it tries to combine them, it's now trying to tack on tracking onto tracking.
Yeah.
And it has a condition. That's why we have this names repair by default to say, hey, not up in here. We're not allowing that. You can't have duplicated column names.
So now when you run those two lines, you'll just get barked in a whole bunch of warnings saying, okay, well, then if you want to do this, we're going to call this column this, and we're going to call that column that. And so there you see play turns into play ... one. The second time it sees play, it turns it into play ... six. It's essentially assigning the column name after three little dots to the name of the column that was specified. We're not concerned with that. It's going to go away here in a second once we do all this stuff. So we joined together using crossing the two tables. We found all of the Cartesian products of all the players to themselves or to their own team and to the opponent. I'm going to use the set names function, and I'm just going to go ahead and name these columns explicitly how I want them named. So the first column names are exactly how they were in the original data set. The second column names are _rel, our relationship, so player relationship. So essentially we have a player and we have the player relationship and we have the team and the team relationship, and then we have the X and X relationship and the Y relationship. And then that play second, that's basically the same play number. We're just going to drop that column. We say adios to that. And then the last thing that we have to do is if you look at row 1 down below, you can see that we have Christine, with the relationship to herself. We don't really care about that. So let's filter out anytime that happens. And then within mutate, we're just going to calculate a little bit of Euclidean distance here. So the difference between the x's and the difference between the y's squared, we sum them together, and then we take the square root of all of that mumbo jumbo, and that's going to report back to us the distance between each player and the players on their team, as well as their opponents. Okay, perfect. Let's see how else we could solve this. Another way to solve this would be to use the left join function. So, and actually, we don't need tracking copy. We didn't need to make a copy of the data
Oh
set.
yeah.
So we're just going to go with tracking. So we have the tracking data. We're going to left join it to itself based on play. Because what's going to happen if we were to just join this without the by comment is it's going to overwrite all of the columns that it finds agreements with, which is essentially everything. So it collapses it into itself.
Yeah.
We
Doesn't
don't
work.
want to do that. So if we join by play, it's going to give us the little an XY assignment.
Yep.
Yeah, dot XY assignment there at the end of each column.
Yeah.
So we know which is from the X data frame and which is from the Y. You can specify the names
Yeah.
specifically if you want to. We just didn't do that here, but you can add a names call in there and
I
say
think
how
it's
you
like
want it.
suffix or something like that.
It is, yeah.
Yeah,
There it is.
suffix. And so you
So
could
you could do, keep
leave that
the
blank and then
leave that
call
one
out
blank and
rel.
do underscore rel. Yeah. So then
Yeah.
now it'll essentially look exactly the same. Again, we're going to filter out anytime the player and the player player relationship is the same because we don't care about that. The distance is going to be 0 because it's a player to themselves. And then we just did a little bit of an arrange by player. Oh yeah, throw the distance function in there. We forgot that. X dot X and Y dot Y. X dot X. Yeah, there we go. And
No, it'd be that, right? No, am I? I was
it's
right.
going
I
to
was
be
right.
X dot X. Yeah, and X dot Y, and then Y dot X
That's
and
not
Y.
confusing whatsoever, y'all.
No, I know it's like super silly. But if we run this, we're going to get the exact same output. And so this is a simple, easy way. Both of those methods work to take your tracking data and basically start to look at the relationship between players and their teammates or players and the opponent within a given play.
So you
And
can
then you can do analysis from there.
start to expand how you're doing, see how this works out across multiple plays, and see what's going on, and start performing your analysis. So yeah, that is a way that you can
Yeah.
use crossing in one way, and the tools that exist in crossing, as well as some other tools like left join or some other stuff in our tool belts to approach your data and your player tracking information.
Yeah. Cool. That's what we
So
got.
so with that, I guess we're gonna call it done for episode 123. Thank you all for joining us so much. As always, my name is Ellis Hughes. You can find me on Twitter at Ellis_Hughes.
And my name is Patrick Ward. You can find me on Twitter at OSPPatrick and at tidy_explained is where we both are on Twitter. Of course, you can email us tidy.explained@gmail.com. Most people love to get in touch with us by liking and subscribing on the YouTube channel and dropping the comment down below if there's an issue that you're currently dealing with cleaning data in tidyverse and you maybe want some help. Hit us up and maybe we can use the example on air or use a toy example similar to what you're working with. And as always, we're always appreciative of those who feel like we've helped them and they want to contribute. And if you would like to contribute, we do have a Patreon page, and anything that you contribute is always greatly appreciated.
Yeah. Thank you all so much, and keep on exploring your world. Bye.